Good evening, I'm Alexandre Coninx, and I will give you a short talk on some work I did when I was at Imperial College London in the personal robotics lab. I'm not working there anymore, but it's part of the work I did there. I'm not a deep learning expert myself. My background in the beginning is in robotics and computational neuroscience, but I will give you a short talk about a machine learning application that's maybe a bit unusual compared to things we are used to see, and that popped up when we were researching something for human-robot interaction. So it's about applying deep learning to human posture data classification. So human posture information is a quite popular research topic since we have those Kinect and Access action, which are very efficient and cheap depth sensor that give us that kind of depth image. So it's a depth snapshot of a scene. So what we want to do is get this as input. We have one image or maybe a stream, or a video stream of maybe image, and we want to get information on what the humans and the image are doing, and some information that's relevant to what we're trying to do. In robotics, it's quite useful to see in human-robot interaction. We want to know how to optimize the human-robot interaction based on what we are seeing. So it's actually a quite complex problem. There are two sub-problems. First, it's extracting skeletons from depth image, so it's image segmentation, user localization, and then skeleton extraction. Its techniques quite alike to classical image processing and computer vision. It's quite well addressed by the literature. And once you have the skeletons, there is a problem of what to do with the skeleton information, how to get some information that's relevant to what you're doing. And that's what I'm going to focus. What we want to do is identifying and characterizing things like motions, gestures, postures, and getting as much information as we need for them. There are many possible applications, including robotics, I was mentioning. And the problem is that it's very task-relevant, task-dependent element. So, where are we in data extraction from skeleton data? There is a lot of work focused on identifying stuff. For example, identifying gestures in the video sequence, people drinking or shooting a football or something like this, or classifying postures, like different discrete postures, and people are basically treating that problem as a multi-class classification problem. And they use classic machine learning techniques to solve that problem. The problem is that I said that I did that work as a robotics researcher, working on human-robot interaction, and that's not the kind of thing we're interested in when we're doing robotics. What we want to do is information that inform us about what the human is thinking, is doing, how he's feeling, if he's feeling good or bad about the interaction, in order to make the robot behave differently according to that. So, and that we can get from the posture, because posture is rich with non-verbal information. For example, you can see that she is very angry. You don't need the renditor for this. So there is the problem of extracting this worth of information about the emotional state, social behavior, that kind of thing, from postures. And this is not the same problem. It's about having a set of labels, of things we want to evaluate in the posture, and evaluating each of them. So it's a multi-label classification problem. You have many labels that may or may not be present. So how can we approach this problem? Well, we won't jump directly to the conclusion and try to do social and emotional classification, because we're not that good and have to. So we start with some kind of a toy problem. Oh, well, there should be skeletons here, not just blue dots, I'm sorry. So basically what we are working with in that work are high-level descriptive labels, which are not just specific postures we want to recognize, but things that can characterize a posture, like someone taking a big stance or a small stance, or something curved or something spiky. What's interesting is that some of these labels are incompatible. For example, you can't have a position that's both big and small, but some of them are not. And so you have individual labels or collections of labels. We worked only on pairs of labels, but we could do more. For example, something both big and spiky. So that leads us to the problem of multi-label classification. So multi-label classification formally is given a set of labels with more than two labels, at least two labels, learned from examples where each example is associated with a subset of the label set, and not just one label. So it's used in quite a few applications. The two biggest ones are probably text categorization about topics, for example. You have more than one topics per text. Functional genomics too, when you want to link protein or genes to different theoretical process. And more generally, plenty of things in biology and in natural science. So you have two very classic methods to solve that multi-label problem. The first is to treat it as many separate binary problems as you have labels, or to treat it as a multi-class problem with the power set of the label set, which means you consider each possible case of each possible collection of labels as a different possibility. But the problem is that those two possibilities don't take at all into account the fact that you can have correlations between the different labels. Some labels may make other labels less likely or even impossible, or basically affect how you can consider the problem. So you have also dedicated multi-label approach. One of the most popular one currently is based on random forest classifiers. So it's not working. And multi-label perception. So yes, because multi-label perception, of course, are naturally multi-label classifiers. You can just put your label collection in the output layer and train a logistic regression or whatever thing you want. But the problem is that simple multi-layer perception with shadow classifier are not well suited to proto classification. They usually perform quite badly. Why? Well, probably because there is quite a few filters in input. There is 76 input filters, which are just relative positions and angles of various joints. So it's something that really has to be taken as a whole to build intermediate filters from which you can get a meaning. So basically it's not working, and indeed they are not very much used in the literature about skeleton classification, and when they are used they are usually overperformed by other techniques, like, as I was saying, random forest. So what I was trying to do is say, let's try to apply deep learning to that very problem, to try to solve the limitation we see with material perception. So we tried, I'm trying to go quite quickly across the technical details because some of it is still work in progress and some of it is not published yet. But basically what we want to do is use text autoencoders, which allows us to take advantage of a very large unlabeled dataset, because the training set, of course, has to be labeled manually, and that takes a lot of effort. But on the other hand, it's very easy to get lots of unlabeled data from the Kinect sensor. We just put a Kinect and tell people to do some random posters in front of it. And so we can get some relevant high-level filters on which you can get supervised training, and we compare it with other state-of-the-art methods from the literature. So I'll just go very quickly through the content. So basically, it's I don't know how familiar you are with autoencoders. Autoencoders are neural networks that learn to reconstruct their own input with some constraints of the structure of the training rules that make the filters they learn interesting. And they can be learned layer-wise. So basically, we learn the first autoencoder as a shadow classifier, and then we can learn many layers iteratively by teaching each layer to reconstruct the input of the previous layer. So it's just basically the classic way to train an autoencoder. And then we do supervised training and fine-tuning to learn the label set themselves. We used a few tweaks to make it work better on multi-level datasets. For example, we use quite specialized error functions, which make more sense for multi-level datasets. Basically, what we can get is we see that our stacked autoencoder approach with the multi-level system works better than quite everything in the literature. It overperforms the random forest classifier, which are usually among the best for the generic multi-level classifier for most multi-level problems. And it's much better than the shallow classifiers. And well, super vector classifiers are not very good for that, but I just show them as a benchmark, as a baseline. So, well, what we did is just classifying some people doing some spiky or big or short shapes. It's not very impressive yet, but we showed that we can use multi-level classification, can use stacked autoencoders and deep methods to efficiently label postural data with multi-level classification. So now we want to apply it to more directly useful for robotics and more abstract filters. Like the one I was saying at the beginning, but we don't have the data for that yet. Basically, it's quite promising for human-robot interaction, and there was research about an application about how to evaluate human behavior from this postural data. And yes, and since I was saying it's quite easy to get some Kinect data, and there are quite a few databases on the internet of that kind of data. Maybe it could be interesting to see if we can get even better representation by using much better, much higher, much larger database and trying to find some invariance. So basically that's it. So if you have some questions.
What is the size of the input data?
The supervised dataset is about, if I remember correctly, about 6,000 frames from something like 15 different subjects.
15 different labels?
No. You know, the input data or the
input data, and then after is the output.
The data set is about, the supervised dataset is about 6,000 frames, so 6,000 skeletons, okay. With each associated to a collection to a set of labels.
So you were showing a ratio of 1 to 12 to the 12.9 number of labels as opposed to unlabeled. So that's basically you have 13 more images and skeletons.
Yes, that are not labeled.
Labels.
Yes, so I have 13 times dot 6,000. I don't remember. Well, you do the math, but they have much more unlabeled data than labeled data.
So about 100,000.
Yes, something like this.
Okay. Well, the size of the input data is about 76, from what I understood.
Yes. The vector size is 76.
76. Okay. And then the labels are.
It's only 5 labels.
How many?
5. It's a 5. It's a 5 posters, 5 filters we were striving to recognize.
Okay. All right. Thanks.
Welcome. Yes. Sure. So, well, you first, okay.
So, have you tried variants of autoencoders like adding sparsity, complexity, and contractive autoencoders?
I don't try the contractive ones, but I consider doing it, and then I adopt the idea. But I think it should be a good idea. Those encoders, they use sparsity. Basically, well, I tried with and without sparsity, and sparsity gives better results. And another thing I tried is adding noise to do the denoising autoencoders. But I expected it to perform better because Kinect data is quite noisy. But actually, it's not significantly better. Yes? Yes.
Well, the output from that you're getting from the Kinect is already the result of the random forest algorithm that is inside the Kinect. Don't you think that you would be doing a better job if you were to be going directly for the 3D map that gets out from the Kinect as opposed to relying on the random forest and then adding on top of this some autoencoders? What's your views on that?
Well, I don't really use the random forest as a Kinect, but it's the same. I use the random forest from the OpenAI and Night frameworks, if you're familiar with it. But actually, I get the image from the Kinect and I feed them to a library that do that kind of pre-training for processing work. But I think I'm not sure I would really be getting some better data because I'm really interested in the poster itself, how it's described by the skeleton. And actually, the libraries already do quite a good job at extracting the skeleton. And well, besides, it completely turns the problem into a computer vision, pure computer vision problem. And actually, the Kinect has quite bad spatial resolution. I work with the old generation Kinect. I didn't have the new one yet when I did it. So I don't really think I could get so much things directly from the data image data.
My concern is if Kinect were to change their algorithm, their random forest algorithm, to essentially devise a better skeleton describing type of algorithm, to what extent do you think that your autoencoders would essentially fail at these new type of sets of data once you've been essentially training?
I mean, how much do I rely on this specific representation? Yeah.
Essentially, you're relying on one random forest algorithm.
Yes, that's true.
And if there is a new one coming up, because the Kinect has essentially a new version coming up and everything.
But that's why I was saying that I don't actually use the random Kinect from the random forest from the Kinect. I use an external library. I use the Night and OpenAI stack, which have some random forest. Well, they could change the implementation too, but I can still take that implementation and run it on whatever depth image I can get my hands off, whether they came from the Kinect, from a new Kinect, from another sensing system.
So I'm not understanding the skeleton that you're getting, the skeleton information,
yes.
You're getting it from the OpenAI?
Yes.
Okay, but that information is already something that is processed
within
OpenAI through a random forest type of algorithm.
Yes.
If that algorithm were to change, you think that somehow your autoencoders would be having problems with the fact that you have new kinds of data coming out of the sensor through OpenAI?
That's a good question. I think if I can get the same, I think if the morphology of the skeleton itself remains the same, with the same number of joints and the same human body model, it will just go fine. Maybe even we can mix the data, or maybe we have to do some kind. Anyway, the data from the skeleton algorithm is already quite heavily preprocessed, because not everything from the skeleton is interesting. For example, we don't care at all about where exactly the person is in the image, which frees us 3D freedom. So there is already all kind of preprocessing doing on that data. Probably that preprocessing should be adapted, but I'm quite confident unless the skeleton shape completely changes, it will work.
Thanks.
Welcome. Okay.
Yes, I have a question on the autoencoders. Namely, how do you evaluate the quality of the features you get, and how do you choose how many layers you have to add to get satisfying features for the problem?
Okay, the first question is about the evaluation of the result. Okay, well, okay, the evaluation of the result, you have quite a lot of metrics you can use to evaluate multi-level classification. The percentage I was showing are quite simple. There's the Hamming loss. So it's the Hamming distance between the predicted level set and the real level set. You have quite a lot of measurements you can use to assess different aspect of the multi-level problem. It's quite detailed in the multi-level literature, and I modeled those things too, and they perform. My autocoders perform quite well according to this. Other measurements too, but the Hamming loss is one of the most standard and one of the most easily understandable for people who are not familiar with multi-level classification. About the number of layers and the parameters, well, I just did a research. So I tried many number of layers, many size of layers, different parameters like sparsity or noise constraint I was mentioning earlier. And the one which worked better currently have 3 hidden layers. I don't remember exactly how many filters they have by how many nodes they have by layers, but it's something like the order of magnitude is a few hundred, and I have the sparsity constraint.
So to choose a number of layers, you do the whole pipeline. So you extract the features and then run the classifier.
Yes, I run the classifier on many times with different parameters, and I did the whole training. It's actually, well, I didn't mention it, but it's implemented using theano. And I ran it, well, depending on the number of layers on the side, of course, it trains in a few tens of minutes to a few hours on a big GPU. Yes?
What is the split between the unsupervised pre-training part and the fine-tuning? How long do they...
I don't have the exact figures in head, but the fine-tuning part is much longer. The fine-tuning is much longer, yes. The unsupervised training is actually quite quick.
Right. One last question.
You have,
Is the data set available?
yes, it's not available online right now yet, but I plan on making it available once this work is published in somewhere in the scientific literature. And well, I can make it available if you want. I can give it to you. Yes.
Thanks.
You're welcome.
All right. Thank you.